Alright, what is up, everybody? Week 6, right here. I know I'm one day late. That's because I had to study real hard yesterday for an exam that I'm gonna have Wednesday. So yeah, I didn't exactly have time to upload the video. So I'm uploading one day later. I hope that's okay. Anyways, let's go straight into it. So, linear algebra. I continued learning about transformation. Now, if I remember correctly, I talked about linear transformations last week, in which you have a transformation of a vector space into another vector space. So you can express the vector spaces this way, in which the transformation takes one vector from a vector space to another vector in another vector space. Sorry. And okay. Okay. Now, what I learned this week, though, was something completely new, which is the kernel or the null space of a transformation. So, like I said, transformation takes one vector from one vector space to another vector space. Now, the kernel or the null space or kernel of a vector space, I'm gonna put like a V. You can see them like this. No, it's not. It's not of the space. It's of the transformation of a vector. You can see it like this. Is when you have a vector space here, you have another vector space, and you have a set of vectors here, okay, that when you transform them through that transformation, you always get the null vector, okay. This right here is the null space of T, okay, or the kernel of T. So it's all the vectors in V that when you transform them, you get the null vector in W, okay. Now, I actually happen to have an example here, okay, to make it a little bit more understandable, in which I have a transformation. Sorry, I have the transformation of the three-dimensional space into the three-dimensional space, and it's defined like that: x, y, and z. Take x, y, z, and I get x plus 2y minus z, y plus 2z, x plus 3y plus z. Okay, that's the transformation. And then he asks for the first thing it asks is the null space of T, the dimension of the null space of T, which is basically how many vectors you have in that subspace, and a base of the null space. So to start off with the null space, like I said, it's the null space is a set of vectors. When you transform them, it must give you 0. So that's basically, in practice, that's basically you take x plus 2y. In fact, just gonna copy this like this. You just take all of this. And you put that equals to 0, 0, 0. Of course, because this right here is a transformation, but it's supposed to be 0, okay? And then what you're gonna have a rule for all the vectors in V to follow if they want to be part of the null space, okay? You're gonna see it right here. So this gives you a system in which x plus 2y minus z is 0, y plus 2z is 0, and x plus 3y plus z is also 0. From here you get that y is minus 2z, from here you get that x plus minus 6z plus z is 0, which tells us that z is 5z, okay, because this right here is going to give you minus 5z, so this is going to be 5z, and then here you put them here, so 5z plus minus 4z minus z is 0, okay, so this is minus 5z, so we're gonna have 0z is 0. So when you have something like this tells you that z is a free variable. This means that all the other variables x and y are going to be given in function of z, okay? So okay, so the solution, okay, the solution of this is that x is 5 gamma, y is minus 2 gamma, and z is gamma itself. Okay, what does this mean for the question? What is the null space of V? It is the null space of T, which is the same thing as the kernel of T. It is a set of vectors x, y, and z in which no, I'm sorry. I always get confused in this final part here. It's a set of vectors 5z minus 2z z, okay, for z being a real number. You can also put that as z times 5 minus 2 1 for z being part of the real numbers. Okay, so basically it is you can have all the vectors in the null space of the transformation if you give a simple z. So if z is 2, you can have the vector 10 minus 4 and 2. That's a vector in the null space. If z is 1, you're going to have 5 minus 2 1 and so on. And that also leads us to the second question. What is the dimension of the null space? The dimension of the null space is given by how many free variables you have in your null space. In our case, we only have one free variable, so that leads that the dimension of the null space here is 1. Okay, and the last question is what is a base for the null space? For you to get a base in the null space, you just have to set a value for z. So for example, for z equals 1, you have the base 5 minus 2 1. Okay, for z equals 2, you're also going to have, for z equals 2, you're going to have 10 minus 4 2. Okay, so the base of the null space in transformation, you can say that it's a set 5 minus 2 1 10 minus 4 2. Why? Because you can express any vector in the null space through a linear combination of these vectors right over here. Okay, all right, now still following the same example, we have yet another question here. What is the image of the transformation? What is the dimension of the image of the transformation? And what is the last question? Let me just check here real quick. Of course, and a basis for the no, not the null space, for the image of T. Now, what is the image of T? If you go back again to this vector space that we had before, now instead of the subspace being here, it's going to be on W. Okay, so it's going to be a set of vectors in which they're going to be basically the answer, okay, the answer to the transformation of all the vectors in V. Okay, so what does that mean? You can say that the image of the transformation is a set of vectors A, B, and C, because W is part of the three-dimensional space, so is V. Wait, sorry. In which the transformation of a vector x, y, and z that belongs to V is A, B, C itself. Okay? So what does that mean? We saw up there, let me take it. We saw up there that the transformation of x, y, and z is equals to all of this here. So what I'm gonna do here is I'm going to take all this here, I'm gonna put down there, and that's gonna be equal to the image that we have, A, B, C. So that's yet another system. So x plus 2y minus z is A, y plus 2z is B, and x plus 3y plus z is C. From here we have that y is B minus 2z, and then you put it over here. We're gonna have x plus 3b minus 6z plus z is C, which leads that x is C minus 3b, and this over here is gonna give you minus 5z, so plus 5z. Let me check. X does it equal right here? X is C minus 3b plus 5z, yeah. And then you put over here, I don't know why it's laggy. I'm gonna have C minus 3b plus 5z, which is x, plus 2y, so that's plus 2b minus 4z, minus z, that's A. And then you can cut a few things here. So 5z minus 4z minus 5z, so that's minus 4z minus z, that's minus 5z, plus 5z, that's 0. So you cut that, and you cut that. And minus 3b plus 2b, that's going to be minus b. Yeah, you can't cut anything anymore. So I'm going to stop here. You're going to have that C minus B is A. Okay, that leads that A plus B minus C is 0. So now we have a relationship between the numbers in all the vectors in the image. Okay, so you can say that the vectors in the image, okay, so that's the vectors that belong to W, in which they are like the answer for a transformation of the vectors in V. They need to follow this rule right here. The first number in the vector plus the second number minus the third one must be equals to 0. Okay? So you can say that the image of the transformation is a set of vectors A, B, C that belongs to W, in which A plus B minus C is equal to 0. Dimension of the image. Again, let's see how many free variables you have. If you put this, if we isolate A, you're going to have that A is C minus B. Here we have 2 free variables. So that leads that the dimension of the image of the transformation T is 2. Bases. Again, we're just going to have to assume a value for the free variables. So let's suppose for C equals B equals 0. You're gonna have one of the bases. A is gonna be 0 minus 0. That's gonna be 0. C is 0, and B is 0. Now that's I know that the null vector. So that means that the null vector is part of the image, of course. because it needs to be the answer for the transformation of any vector in the null space. That makes complete sense. Now, for C equals 2 and B equals 1, you're going to have the vector A is going to be 2 minus 1, which is 1, B is 1, and C is 2. So that's yet another vector. And it follows, it is part of it is part of W because it is a three-dimensional vector, and it follows the simple rule. A plus B, which is 1 plus 1, minus C, which is minus 2, leads to 0. So 1 plus 1, 2, minus 2 is 0. Okay? So you can say that the vectors, the basis for the image of T is this set of vectors right here. 0, 0, 0, 1, 1, 2, and there's a lot more. Okay? This means that any vector in the image you can express through a linear combination of these vectors right there. Okay? Now I would talk about, what's the name in English? I would talk about injective and surjective transformations, but I already got what they were when I was studying it, like Wednesday or Thursday, something like that. But I already forgot, and I tried to study it a little bit briefly before I made this video, but I didn't really get it. So yeah, I think I can't say that I've really learned it because I can't explain it to y'all. So I'm gonna leave it to next week, okay? And now I'm gonna go to calculus. Okay, calculus. I had a little bit of problems finishing a part in Khan Academy. I had, Khan Academy has those little axioms, and I was always failing in at least one question, and that made me fail the whole test, and then I had to do all over again. But in the end, I understood everything pretty well. But what I truly learned this week in calculus was about continuous functions in intervals. So kind of a continuation to what I learned last week, and it was actually something that I didn't learn when I took my calculus 1 classes in college. What is it? Well, if we assume a graph here, and you assume a function like, let me take a blue. Let's assume a function like this, okay? Kind of like a sine function, kind of. And then you have this right here is 5. This right here is minus 5, okay? So we are looking at the function in this interval right here. And then it asks, is the function continuous in this interval, minus 5 to 5? Is it continuous? Now you look at this and say, of course, like Khan Academy likes to say, I can draw the function without taking my pen off the paper. And that would be correct. Of course, the function is continuous in that interval. That's pretty easy. Okay, now let's put, let me take a little bit here. And let's put a empty circle here. Now, if I asked, is the function continuous in the same interval, I would say no, because there's a hole in the function. And if you like to say how Khan Academy likes to say, I can't draw the function without taking my pen off the paper. Okay, that is also correct. Another pretty easy example. Now, if I have a hole right here, okay, the function is not defined over there. Let me just make it easy for myself here. is the function continuous in that same interval from minus 5 to 5? Now, at least my old self would say no, because the function is not defined in minus 5. But the correct answer is that the function is indeed continuous in that interval. Why? Because when you have parentheses here, okay, that means is the function continuous in an interval like this? You have 5 here, let's say you have 0 here. Is the function continuous in this interval right here, but it doesn't count 5, neither minus 5. Okay, so it's like between minus 5 and 5. Its values that they are greater than minus 5, but they are smaller than 5. They don't count minus 5 and 5. And here you can see that the function, it only isn't defined in minus 5. Okay, so it doesn't exist f of minus 5. Okay, so is the function continuous? Yes, it is, because between minus 5 and 5 it's completely continuous. Okay, now this is different than if I asked you, is the function continuous in the interval minus 5, 5? Now you see, before we were using parentheses, now we're using brackets. I think that's what the name of these things are. We are using brackets. Now when we are using brackets, things change, because we're not talking about this interval right here anymore. Now we're talking about an interval that actually considers the both ends. So now it comes from minus 5 all the way to 5 inclusive. Okay, well, that will be like minus 5 greater than or equal, smaller than or equal to 5. Now when we talk about this, then we can say for sure that the function is not defined. It is not continuous. Sorry. Why? Because an exactly minus 5, and you can be equal to minus 5, the function is not defined. So this means that the function is not defined, is not continuous in a specific interval. Okay, and that was something pretty interesting. That's something that marked me more this week, because I did not know that you could have that type of behavior in a function. They did not know the difference between having parentheses and brackets. For me, it was all the same thing. Another very interesting thing that I learned this week is that sometimes you can have a function that it behaves in a certain way between an interval, okay, but it's not defined for a certain x. Let me try to come up with an example here. I'm very bad at coming up with examples. So let's say the function f of x is x squared minus 4 divided by x minus 2 for x different than 2. That will make sense, because if x equals 2, we're going to have 0 by 0, and we can't have that. It's not defined. But then the function f of x is k. It's something here, k, for x equals 2. What does this mean? This means that f of 2 is k. And then the question often says, okay, what is k? How would you do that? Because it seems a little bit off. But before they ask you what is k, they say that the function is continuous it's very bad writing this thing. Function is continuous for x greater than or equals to, I don't know, minus 12. Okay, so this means that from minus 12 on, this function is continuous, which includes 2. So this means that there must be an answer to k. K must be something. Because if the function is continuous from minus 12 on, this means that if we look at the graph of this function right here, we are going to have a minus 12 here, and we're going to have, I don't know, like 2 here, and the function, I don't know, maybe no, it needs to be defined here. Okay, so we're gonna have, so it should be something like this. So this means that there is something here, it is defined at 2. Okay, how do we look at that? How do we calculate that? And that's when limit enters the game. So we calculate the limit of x tending to 2 when x of x squared minus x squared minus 4 of x minus 2. Why? Because then we are looking at what is the number here, what is the y here. Okay, this is going to be k. What is the y? Let me get a little bit closer here. What is the y when we approach 2 by both sides? Okay, since it is continuous, this means that whatever we get here, whatever the limit is tending to, okay, in fact, the function, let me be a little bit more clear. The function is undefined here, okay? In fact, it would be undefined if we didn't have k, okay? Since we have k, then it is defined by k, okay? This is k, because f of 2 is k, okay? I almost committed a mistake right here. We need to find k, and that is going through limits. So, okay, how do we solve this? This is pretty straightforward. This is the difference of squares, I think. So that's going to be x plus 2, x minus 2, so x squared. They're going to cancel out both. They're going to have minus 4 divided by x minus 2. They're going to have cut those two. I'm going to have the limit. Whoops. The limit of x tending to 2 of x plus 2, that's going to be 4. So that leads that k is 4. Okay. Yeah, in calculus and linear algebra, that was about it. Now, when it comes to Python, I'm reaching a phase here in the video in which we're getting introduced to user interfaces with Python, and I'm gonna be pretty honest. To me, it's not being like real learning. It's more like you try to memorize stuff, and you try to memorize a bunch of commands to make the thing work. So yeah, I'm not really positive about actually having learned anything. It's kind of like the injective and surjective transformations thing. I'm not really confident that I learned anything about Python this week, but I'm still proud of me this week because I managed to make. Let me pull it out here. I managed to make a program that does the thing I hate the most in linear algebra. What is that? Gauss, solving linear systems with Gauss. Now, of course, here you're gonna see that it's all Portuguese because I'm actually trying to make this for other students as well. Who knows, it might help them. But this is a system I programmed entirely in Python, okay? And it takes a matrix, and depending on how you set it to be, like if you put 3 here, you're gonna have 2 options. You can either let it let the program solve the matrix, the linear system automatically, or you can do it manually. And I'm gonna select manual here because manual is a little bit more fun. So for example, if we take a linear system, let's say, to make a little bit more realistic, I'm gonna suppose here a x equals 4, y is 8, and z is 1. Okay, and then from here, I'm gonna take a linear system of 3 by 3. So 2x plus 7y, that's gonna be 8 plus 56, that's gonna give us 64, right? And 8 plus 66, yeah, 64. If we take y plus 8z, that's gonna be 8 plus 8, that's gonna give us 16. And if we take 4x plus 2y plus z, that's gonna give us 16 plus 16, that's gonna give us 32, plus 1, that's gonna give us 33. Okay, so if we didn't have that, this would be a real system to solve. Okay, now we can actually put this, if you know how to make this into a matrix, which is 2 0 4 7 8, my bad, 7 1 2, and then 0 8 1, and then 64 16 33. There you have a linear system. This is a 3 by 4, so 3 by 4, and then you put the numbers. So 2 7 0 64, 2 7 0 64, 0 1 8 16, 0 1 8 16, 4 2 1 33, 4 2 1 33, and then it builds the matrix for you. There you go, just like we have here. And then you can actually, on manual mode at least, you have a kind of like a command bar here, and then you can run the commands. The commands are add, swap, and scale. Add, it adds a row to the scale of another row. Swap swaps rows, very self-explanatory, and scale scales a row. So to start, I'm gonna actually swap the line 2 with line 3, and that's what we're gonna have. And then you can see, of course, it's English, it's Portuguese, but you can see that we swapped line 2 with line 3. Okay, and if you compare the results, it really did that. Now I'm going to scale the first line, line scale 1 with half, and that's what's incredible. This program, it actually accepts fractions. You don't have to, of course, this would also work if you have 0.5. It worked, but scale 1 2, if you put scale 1 over 2, that's also gonna work. Okay, now add. Now we're gonna add line 2 to -4 line 1, and that's exactly what it did. It took line 2 is gonna be line 2 -4 line 1, and now you got the 0 here. Next step is gonna be we're gonna scale line 2 to be -1 over 12. That's gonna give us 1 over there, and now we're gonna add line 3 -1 line 2. Now finally we're gonna have to scale line 3 to be 12 over 997. And to make it a little bit more prettier, I'm gonna add line 1 -7 over 2 line 2, and then add line 1 -7 over 24 line 3. Okay, and then I'm gonna add line 2 plus 1 over 12 line 3. There we go. So now we are on the most simplified version of the matrix, and as you can see, x is equals to 4, which is exactly what we x is equals to 4 is exactly what we did over here. Y is h, and z is 1, so it works perfectly. Of course, let me exit here. The automatic mode would also work very well. 3 over 4. 27064, but it always follows a a specific algorithm 421 and sometimes it's kind of dumb, you know what I'm saying? And it doesn't do the whole simplified version. It just gives you the minimum that you need to have so you can build the system and so from there. It's not really complicated to make it go all the way to the most simplified version of the matrix. It's just because that I really started this program this week, like Wednesday afternoon, and I finished Friday. So it's not 100% yet. I'm still cleaning possible, wrong inputs and stuff, and then I'm polishing the thing, and then I'm gonna put it in our GitHub repository, and who knows, make it available for everyone. It's gonna be my first open source program. So yeah, even though I didn't really learn anything from Python, like truly something besides that interface stuff, which just kind of memorize commands, I did something really useful for myself at least. So yeah, I would say I kind of did something good with Python this week. Yeah, that's gonna be about it. Again, sorry for not publishing yesterday, and yeah, have a nice one.